Okay, good morning everyone. Did you have a good evening? Are you still full of energy? So I think what we want to do today is to make good progress, finishing discussing at least the key unitary test, then move on to co-integration and see how far we can get, if we can even get to estimate an ECM, the final step in the process. So we didn't completely finish yesterday all these statistical processes, all the ingredients that we need to understand how to look at realized economic time series, published economic time series that we deal with. So what we want to do is, where do we start? We get a series. You identify your model, you do a lot of reading, you try and understand your problem, you see what other researchers do on the matter, and you then have kind of a model specification that you think is a good starting point. That's almost never your final model specification. Along the line, we learn more, we try more things. There's often in the literature a couple of rival models which we then want to try and test. And sometimes the textbooks don't tell us, it tells us that, or textbooks tell us that risk matters, sentiment matters, all of these things. But then what would be the best sentiment, confidence, risk measure? So there's a lot of work going into that. And once you have then collected, you've specified your model, the functional relationship of, you think, which are the most important determinants of what we look at. Once we get there, you search and you collect your data. Then what is the best source? Where do we go for these things? If we think institutional quality matters for our analysis, there's so many different measures. What would be most appropriate for what we do? Is it regulatory quality? Is it the rule of law? Property rights protection? Is it the freedom to trade and take your own life decisions? Is it constraints on the executive? How can government just do what they want, or are there constraints on what the powers that be can do? So then you can, then you start collecting data and you have everything now collected here. And you say, okay, I will see, maybe I will use a composite index for institutional quality, and then you can decide, how do I weigh these different aspects of institutional quality? Is it just a equal weighted index, like the Fraser Institute does with the freedom of the world institutional quality variable? Or do you want to be more sophisticated and using like a PCA, a principal component analysis that will put more sophisticated weights on components? Or do you even want to do a recursive PCA? You see, so there's a lot of work that you can do, and sometimes for some projects, that is already one paper. If you want to have an index that represent the monetary conditions of the country over time, or financial stress. So that's already just one paper to say, I have constructed this index. Nowadays, there's a lot of work being done by scraping the internet, or looking at some of the polling that's consistently going on. So, and then construct the index from there, representing consumer confidence or business confidence or just general. Typically how it works is that we define certain keywords and have people search for these keywords in a certain period. And we use that to have some indication of how all these economic agents will react to certain situations. So when all of that is done, then what we discuss now, we take a step back, and now we have to, for each and every variable that will go in there, we have to take a decision whether that series is stationary or non-stationary. So it's literally like ticking a box. And if we're going to have the log of the exchange rate as our dependent variable, and we're interested maybe in the rand US dollar, the spot nominal exchange rate, and we know that the dependent variable of the theoretical model specification is log, then we investigate log of the exchange rate. It doesn't help to perform a unitary test on the exchange rate itself. The variable that's going in our model, that's what we're going to put on a graph, do a scatter plot to see relations with the independent variables. We're going to perform unitary testing on that variable. And in the end, we want to make a conclusion about that variable. What is the log of the exchange rate stationary or non-stationary? And secondly, if we say it's non-stationary, then we want to say, is it integrated of order 1 or integrated of order 2? Why is that important? Because when we run the long run, everything in levels, it doesn't matter if it's integrated of order 1 or 2. Not completely, because it helps us to understand, can we expect co-integration or not? But why do we want to know if a variable, if it is non-stationary? Finally, in our final model, we want to use it in a stationary form. So that means if we found it non-stationary but integrated of order 1, that means when we're going to finally use it, we're going to difference it once. And if it was explosive to start out with, exponential trend, we will have to difference it twice so that it becomes a stationary process, and that goes in. So it's only in the final step where if we set up our error correction model that matters a lot. But in the first step, at least for the residual-based approach, it helps us to see, can we even expect co-integration here? Because one non-stationary variable and one stationary variable will not give us they cannot co-move, because this guy is going that way, this guy is going this way. It's not like two dancers on a dance floor. It's like maybe some of those silent discos. Everybody's got earphones and they do their own thing. That's not a co-moving relationship. So if we see we have a variable trending and another variable trending, there is a possibility. If there's a variable trending and a variable trending and one with that stationary, yes, that can still have a co-integrating relationship. So that's where we use it at this stage. How we practically do it, we take all the data that we've downloaded or collected or whatever the case may be. For time series, it's a long period. So it's very likely that you have downloaded it from a source. Otherwise, you cannot wait for 15 years or 20 years to collect your own data and finally then run your regression. So we kind of work with secondary data in time series. So what we do then, we look at graphical depictions of all our series as they will go in the models. Not money, because money will in any case look a little bit like a second order, a variable of second order integrated of order 2. So we take the log and we look at all of that, and then we take a step back and we use all our statistical knowledge and we say this series looks a lot like a random walk. And we know, but then we know a random walk is non-stationary because it has a increasing variance. A random walk, strangely enough, has a constant mean, but increasing variance. If it looks like a random walk with drift, then we know what the properties are. And we know a random walk with drift is a non-stationary process. And if it looks like a mean reverting process, then we know that series is stationary, and in later steps we don't want to difference them. So yesterday we looked at the properties of a stationary process. So no subscript, and then not a t, but only depending on 4 quarters, if k can be equal 4 or 12 or something like that. And then the white noise process was simply where we have 0 mean and a 0 covariance. So really that random idea. So when we get to a random walk, now so that parameter now is a 1, and just to show that it's not so obvious if you see series trending, a random walk series trending like that, it doesn't feel that series, we can claim a constant mean for that one. If we look at it from this mathematical perspective, what are we dealing with? If there's a 1 there and we do some back substitution, so the yt minus 1 is then equal to the previous period lagged y and that error term, and we keep on back substituting up till the initial value. And this will typically be, if your data starts in 2000, that will be the 2000 observation. And if we then take expectations both sides, we see that the expected value of a constant is just a constant. So that the mean is the expected value, the initial value. So for a random walk, it is so random that the best bet expectation that you can have is like it will wander around, crossing that initial value a couple of times. And that is then your expected value or your mean value. Similarly, if we think about the second moment, the variance of a constant is 0, but these error terms, they all have a variance sigma square. And so each time you add one more period, the variance is actually increasing. So that is what makes a random walk a non-stationary process. And those I have simply generated. The code is, if it's not below this slide, it's in the previous unit. you give it a seed value, which in this case was 0, but it will never show the 0, because the first time you generate an observation, it is then y1 and not y0. So they both started there. And then you just use a random regenerator. And then each time you run the set of code, just 3 lines or 4 lines of code, you get two different series. And this is what was done in that work by Granger and others, where they generated 100 sets of 2 variables for 50 periods, and then found in more cases than would be expected, they found series. I specifically chose 2 that worked in opposite directions, but it's still possible to find a negative relationship that appears to be significant. I don't know how many of you play around a little bit with it's probably a good time now to invest in some some equities. But what happens here, especially on just like one period ahead, is literally the price of yesterday plus some random effect. That will fit in the very short term a little bit better than any structural model where you want to put some fundamental variables there, but maybe to have a longer term view. It is good to look at what happens in the bond market, what happens with the economies in general, etc. But this is one of the examples where a random walk, when you forecast, often outperforms any structural model. It's always the benchmark. If you read forecasting papers on currency markets or stock markets, there's always a result for the random walk, which is then the base or the reference. So now, I mean, I think we know these things, that we can prove them, and maybe we can ask the Pelu to take us through that. But we can prove that for a random walk with drift, the mean value, the expected value, will be an increasing value. And then the variance will also be increasing, and so will the covariance. Sorry. So there's just an example of a random walk with drift. It almost resembles which series? The series where the y is simply a function of time with a deterministic trend. That's why when we start doing unit root tests, we make provision for the fact that there can be a stochastic trend, like, a stochastic trend just like this. But if we are honest, many of the macro time series looks more like this. A random walk can also give us this occasionally, but a random walk with drift will almost always increase as a function of time. The mean value is what we see here, the initial value, and then some time function of the mu. So sometimes if you just look at something like the log of the GDP or the log of the money or any of those series, it's hard to tell, is this a random walk or is it a random walk with drift? But it doesn't really matter. that's why when we do the unitary testing, we allow for the possibility that it can have those elements. And this is just a summary across. So the central two columns here shows the properties of stationary, or if we say stationary, we mean weakly stationary or covariance stationary. And those are the properties: constant mean, constant variance, constant covariance. Non-stationary, the mean may or may not be constant. It's only for the random walk that it can be constant. Otherwise, it's time varying. The variance and the covariance are not constant. It depends on time. And here it can be either I1 or I2. A random walk is a very specific non-stationary variable. And then white noise is a very specific weakly stationary series. So in order for us to know how to even better look at the properties of the univariate properties, we know that if you see a series like the GDP, or interest rates, or stock prices, or whatever the case may be, you can fit an ERSA model to that. And strictly, that series can be best described if we only describe it with elements of itself in a univariate setup. Can have AR components, autoregressive components, that's lags of itself. Y can be a function of yt minus 1, yt minus 2, up to yt minus p. And we use model selection criteria to tell us how many lags are best. It can also have moving average terms. That is lags of the error term. And then again, we fit these models. A series can then either be stationary or non-stationary. So for non-stationary series, we refer to a RIMA, where we then first difference the series and then fit the AR model. So in general terms, we refer to the RIMA PDQ, which is if the series is stationary, that means the D is 0, and that is sometimes then omitted. And then P will be if the order is if 4 lags matter, then P will be 4, and if we include 6 MA terms, it will be, and for a non-stationary series, it will then be a RIMA 416. I think that's what I said. And as Shorter's asked, is there room for this in analysis? Yes, definitely, especially for the high frequency models where you just need to have a value for tomorrow. So any kind of time series model, even as simple as a moving average or a more sophisticated ERSA model, can be useful to project future values in the shorter term. So whereas the autoregressive, the component is exactly that. It measures that persistence, the autoregressive or the temporal dependence of the series. How much does t-1 matters, or t-2 for that matter. And then the moving average captures noise or fluctuations in the series. And there's just again the idea that the I is actually relevant for non-stationary series. So what what will happen in the background is that the ARIMA model will be fitted to the different series to see how it fit, and then perform the forecast on the levels result. So that is, in general terms, an AR model. So that parameter can be 0.5, 0.5, 0.8, 0.9. As soon as it's 1, then it's a specific AR model. Then it's the random walk. And note that this parameter can be negative or positive, which will indicate whether the series will trending upwards or downwards. Just to write it in terms of lag, if we just bring this to the left-hand side, so this will be, and then the lag is 1, so it's L with a superscript 1 there, then we write it as 1 minus theta L yt equals to the residual. And then, of course, we can generalize for higher orders, an AR2 process or an ARP process. And then if we apply the lag operator, then now you can see why it's useful to just write it in terms of the lag operator, because we can just write A of L, and that means all of those lags. In terms of the MA model, so now there's no autoregressive component here. It's simply now modeling the noise, the component that we can't explain, and then how much do the past noise matter for today. Up to Q. So now we have the lag operator on the right-hand side, and that is representing all of that. And if it's then an ARIMA model, now we need to lag the Y's for the AR component, lag the error terms. There's the constant, the current period error term, so that in very short notation, we write it as the lag structure of Y as a function of the lag structure of the error term. So that's the most flexible time series model that we can model. We can also bring in, this now brings us closer to structural VARs, where we can also bring in a second variable, and we can lag that variable as many times as we want. And this is now what we do when we do structural VAR modeling, and that's where we mentioned earlier, sometimes we difference the variables and we just run it on the difference variables, especially if it's a reduced form VAR. Not so much for a structural VAR. When it's a reduced form VAR, it's in any case atheoretical. The system allows for everything basically to affect everything else, the Christopher Sims idea. So that in itself, we talk about that, and then it's, but wait, it doesn't really matter for determining the order of integration. But it's still helpful in terms of looking at the autocorrelation function and the partial autocorrelation function of a variable. So the autocorrelation function tells us how well a variable that's trending upwards, how well is it related to the previous period and the previous period and the previous period. All of the periods prior to the current period that we look at for the autocorrelation value, the function value. In terms of the partial autocorrelation, we ignore intermediate. If we look at the partial autocorrelation for period 4, it will be how well correlated is period T and T minus 4. Whereas the autocorrelation function is how well is, am I going the wrong direction? I keep on going in the wrong direction. I think this is where I make work for Jermaine. Then he will have to, now I have to edit this out. Now it takes 10 minutes of my time. The partial autocorrelation ignores intermediate correlation. So we can see this is like a little bit of a, that the autocorrelation function takes everything in between also into consideration. So if we see this series, already we know that just looking at that series, it's not mean reverting. But now we're nevertheless going to spend 10 minutes to perform a unitary test on it. And that's why one of my mentors once said, I remember that, you know what they say, a picture is worth 1,000 words? And in this case, a picture is worth 1,000 unitary tests. Especially when we started out with unitary testing, it was quite labor intensive. The software didn't give us a lot of pleasure. It was very manual, step by step by step. And then still on the side, you had to look up critical values. So it was really a labor-intensive process where clearly for this we know that this is not a mean reverting process. And the fact that there's a lot of autoregressive behavior there, there's a lot of persistence, a function of previous observations, and that we see here. Of course, the further you go back into the future, if we see that T there, that means that is the autocorrelation between the initial period and period 1. So T and T minus 1. If we put period 0 there, current period correlated with itself, it will be perfectly 1. It's not shown. So this, if you look at the autocorrelation function, and you can see it's simply measuring the association, the covariance of the two periods, T and T minus 1, or in this case, T minus, so this will be T and T minus 2, and the variance of that period. So the further we go backwards, it becomes slower, but it takes a long time for the past not to matter. Whereas for, if you look at this one, there's very little, a very weak relationship with the previous period. It cuts off to 0 and then get values very close to 0. However, if we then look at the partial autocorrelation, typically for a non-stationary period, a series, this is what we see. And the fact that we see this spike through 1 is a very good indication that it's an AR1 process, that we don't need a YT minus 2 or a YT minus 3. So on the side, if you compare an AR1 and an AR2, the AR1 will outperform the AR2. So that's already, if you're just a practitioner, and you're not writing it up for a formal scientific document. But these days, it's also the case that recent papers, don't afford pages to report unit root tests. You just put a footnote and say, all my series are non-stationary I1 except for inflation, that is a stationary process. And that's all that your reader wants to know. The reader needs to know, though, that you know what you're doing when you when you made that conclusion. But if you read all the papers, there will maybe be a full page of unit root test results, maybe in the appendix. But we still put, if it's just a simple application, it's just about inflation and inflation uncertainty, it's just two variables, so then we put a little table for the unit root testing and show at least two different unit root tests. But by this stage, we actually don't really need a unit root test to say that series is non-stationary. And yeah, so just the fact that this autocorrelation function dies off geometrically, and the partial autocorrelation spikes through 1. The fact that it's an AR1 process is a little bit beside the point. Your final conclusion will say, my series is non-stationary I1 because, this is in brackets, because when I difference it once, it becomes stationary. You don't have to say it's non-stationary and therefore it's an AR1. And I often see all these lingo. When people start learning this, they will use all the words. They will say, we integrate the series and now it's AR1. What is wrong with that statement? Many things. We don't integrate the series. We difference the series. Difference is the verb. And then it becomes integrated of order 1. And the fact that it's AR1 is a separate issue that we see in the partial autocorrelation function. So stationary series, when that parameter is not 1, when it is smaller than 1, the question is only, when is it small enough? Is 0.9 a stationary, if that we put a 0.9 there, is that a stationary or non-stationary series? Is it close enough to 1 to have a unit root? We will look at a quick demo just in a minute. We can do that. This is probably not so important, but we know that an AR process will have that decline of the autocorrelation function, gradual decline, and a quick cut off only spike through P, typically 1. And then an MA process, if you look at that and you see the partial autocorrelation decays very slowly. And this one has a spike through, say, 1. That will be an indication now I'm dealing with a MA1 process. And if you see both of them decays exponentially, then that will be most likely an ARMA process. This is, having said that, let's just talk through this and then we demonstrate it quickly. So we've said this now many times. When it, as long as that row in absolute terms is smaller than 1, the series will be stationary. As soon as it's statistically close enough to 1, it will be a non-stationary process, and a specific type of non-stationary process, a random walk, and if it's bigger than 1, it's that non-stationary and explosive series. And now, knowing that, and we know that because if we generate the series, we see the properties, and then we are then in need for some tests that will test it formally. So just to, and you can do it with me, let's just demonstrate that. In that folder, I just want to show you here where I can make it a little bit bigger. In the time series concepts folder, there's a demo data generating process. So if you open it on the folders that you have on your desktop or in your documents folder, you will see there's 2 files. One is a work file and one is a program file. But we can equally do this in R as well. Some other examples are done in R, and below the slides, like footnotes, the code is there so that you can replicate that. So if we go to that lecture and we go to time series concepts and here, so what you want to do, like many of the softwares, the program and the data must be in the same environment. We cannot double-click on the work file and double-click on the program. Then it will be in 2 different environments. So what we do is you can open this by double-clicking if you only have one version of eViews open. So once you have the data, and you will see that here I have already I've already simulated some data. What does that look like? A lot of noise. This one looks like a random walk, and this one looks like an explosive series. So if we here, in order to get this program to interact with this data, you have to go to File, Open, and open that program. So File, Open, open that program, and then you can always, if you keep on working with the same on the same project, you can update your default directory here. Otherwise, now I have to browse for that, just similar to using the project in R. So I just now have to browse to that lecture material and get that folder and then open it. So now I have some data and I have a little bit of code that I can run. And each time, since I use just a random variable to start the series, so I have a value for x in period t-1, and then I just want to simulate data with a parameter smaller than 1, equal to 1, and bigger than 1. So each time I run this, it will use a random, so the series will change a little bit each time you run it. The question is a series with a 0.9, is that really a non-stationary series? Or do I have to be a little bit closer? So you can see you have to, and it, of course, it depends on exactly how many observations you have and if you include a drift term or not. But we can see that you have to get pretty close before we can claim that we have a non-stationary process. So that gives us some confidence that we, although we've said, yes, of course, there is something like a partial integration. So a series can be integrated of all the 1.5, but it will just make practical work quite difficult. So we will need a unitary test that will help us pick that up. And here's just when we know a series is non-stationary, if we apply the difference operator and we see this, then we can say what we started out with was a non-stationary process that's integrated of order 1. And if we started out with something like this and only after differencing it twice, then we will say the series is integrated of order 2. And then, of course, a non-stationary process has a memory that is permanent. A stationary series that gets a shock will quickly forget that shock, but a non-stationary series, it will go on that path. So just when we see these terminology. And I think we have, so now we just need a test that can help us figure out. So what do you think the test, a unitary test will be? We'll simply be looking at that relationship. So what we really, this is actually looking ahead a little bit. So if we already said that when we are going to model with non-stationary data, then we have to be careful with our statistical inference. The t-stats and the f-stats will have non-standard distributions, and the betas will also be non-standard with these fat tails. And that will lead to spurious results where we think we have a good relationship, but actually we don't. So you can see a lot of implications and therefore it is important to spend a little bit of time to make sure what we are dealing with. We already said this, when you have two series that are both stationary, they're moving together. And that is when classical OLS is valid. That's where you don't want to perform a co-integration test, simply because you're wasting a little bit of your time. You can rather go out for a coffee in that time.
Sorry, Prof, just a theoretical question. Say it is stationary and you difference it anyway and you do run your regression on those differences. Is it a chaotic result as well, spurious, or is it valid?
For structural analysis, the only thing that you're then not dealing with the impact of a change on a change. You're dealing with an impact of a change in a change. So you have to be careful how you interpret the result. Okay. If it's just to forecast one period ahead, it will probably do no harm. But even, in the case where we deal with non-stationary data and in the end, the error correction model is in first differences, and then we switch it back to levels to model that, to see what the actual fit is. Because nobody is interested to hear what the difference of the log of money, or what the log of money will be in a next period, or the difference of that. So we always work back to where we started with. So I think in terms of statistical inference, you will do no harm, but the story that you tell is then a story of the impact of changes on changes.
Okay.
When we have integration, but of different orders, that can be an I1 and then an explosive series. That residual will technically also become larger and larger. And if they are then the same order, so this can be so it can even be the same order, like let me just see if I can use my draw with my pencil. In this case, it can be two I1s, but one can trend with a certain slope and the other one can trend with a different slope. They are both I1, but we can see that they are diverging. So that is a case where the residual will then not be that white noise process. And then if it's even of different orders, like in this case, let me do this here, we have one that's linear and the other one that is exponential. So those residuals will be big, smaller, bigger, so it will not be that nicely behaved. What we want is two series that are both ideally I1, and the difference between them, if we regress the one on the other one, will have this nicely behaved. It's not train tracks, so the difference is sometimes little bit bigger and a little bit smaller. And this, we know that this is actually also, if we just do a scatter plot of the one on the other, that is where the variables, high values of the one associated with high values of the other one and low values. So ideally, this is where we want to be. But firstly, unitary testing will help us to know, am I dealing with stationary data, non-stationary data, data that's integrated of different orders, but then this case where you have two I1s and this case where you have two I1s, the one can still be the spurious result and the other one can be the co-integrating result. And sometimes the spurious result is just because you're still missing one variable. Because of all the structural breaks that then causes this residual not to be so well behaved, not to be a white noise process. There can still be then zero correlation present, heteroskedasticity, etc. It must have a constant variance. The mean will always be constant because of OLS, but there might be zero correlation present, there might be heteroskedasticity present, so the variance can be increasing. And I think this is, now we're ready to run those unitary tests. And just to tie it to what we're going to do, everything in econometrics is always, there's an hypothesis, something you believe that you want to investigate. Then there's some econometric activity we calculate the test is sometimes something we calculate, sometimes it's based on a regression, on a test regression. The test is running a regression of some sorts and looking at a test based on the regression result. And that we will then reject or accept based on the distribution of the test statistic. All the test statistics that we use, we force them to be F distributed, T distributed, chi-square distributed, whatever the case may be. And then the implications are sometimes we think the T distribution is that nicely behaved distribution, but it is skewed to the left or skewed to the right or just fat tails or anything like that. So if we could put ourselves back in the 1970s, if we do some time traveling, and you are now the student of Professor Wayne Fuller, and you are, what was Dickie's name? Of the Dickey and Fuller. He was the student of, but long time ago. And you, what you know from statistics, can you use that information based on this to perform a unitary test? How would you do it? You only need Excel. You don't need sophisticated software. What is the hypothesis? And now it depends, sometimes some tests will say the series has a unit root, some tests will say put the null as the series is stationary. But most often we put what we want to prove in the alternative. Not 100%. Of course, there's always that we want subject to the minimizing that type 1 error, incorrectly rejecting the null. So what will be a test of whether that row is 1 or smaller than 1 or bigger than 1? The unitary test is simply running that regression. That's what the unitary test is. Simply running that regression and then do hypothesis test on that row. Say, is that row smaller than 1, bigger than 1? But that becomes complicated, right? So how we will do it, we will say, we will put that hypothesis as row is equal to 1, and we will put the alternative that row is smaller than 1. Because so 1 is the stationary, non-stationary, the trending one. The smaller than 1 is when it has a constant, when it's mean reverting. If you have rejected the null in favor of the alternative, we've rejected the non-stationarity in favor of stationarity. Can it be explosive? We said no, it's not non-stationary. It is stationary. Then it cannot at the same time be, because you've moved from non-stationary to stationary. You cannot then jump that side and say, but maybe it's not, maybe it's explosive. So it's not a two-sided test. This is actually going to be a one-sided test. Hmm?
So that was before ADF test.
This is the ADF test. This is the DF test. They augmented it later, but this is what they did for the Dickey-Fuller test, with some bells and whistles. Like, econometrics is never that simple. Then everybody would want to be an econometrician. And, okay, but how are we going to deal with the case? How will we then ever establish I2? If we just say, if it's not I1, it's I0, how do you then walk that extra few steps to say, so obviously, if say we fail to reject, let me just see if it's now, let me stay here. So what if we started out with this series? So we will ask, is that row, or no, let me do it this way. So if we start out with a series, and obviously if it's trending like this, you would want to reject. But if you fail to reject, then it can be this or this. So that's where you then do another step. If you reject in favor of stationarity, stop. If we perform a unitary test on this one, will we reject the null that it is not non-stationary but stationary? We will fail to reject. Then we difference that series. And if the difference is then stationary, we stop. And if we difference once, we said we started out with a non-stationary I1 series. So if we started out with this one, we will, on the first step, fail to reject, then difference the series, test again, that difference will be a trending series. Now we test that, and hopefully then we will reject in favor of this. But what we then test on the second step is not y, but then it will be delta y. And if delta y is stationary, we stop and we say y is non-stationary and integrated of order 1. However, what are the bells and whistles here? This is a regression. And if we apply it to data like this, what have we said in the previous discussion? That's just a parameter from a distribution. Apply it to non-stationary data, and that distribution becomes non-standard. So if everything goes well, that T will tell us that that row is significantly different from 0, yes or no. That's another thing. Because a standard regression will test it against 0. So it doesn't align with standard hypothesis testing. So that's one thing to address. And how it can be addressed is that we just adjust the calculation of the T to be rho minus 1 over the standard error. So So that's one thing. And the other thing, if we apply this to stationary data, then we can rely on the t-stat there. But if it's non-standard, we cannot rely on the t-stat because the distributions are non-standard, the standard errors are biased, the t-stats are biased, the p-values are wrong. So yes, we could do a run a simple regression, but with the knowledge that the distribution of that row will be non-standard, so we cannot just quickly look at the t-stat and make a decision. That's the biggest takeaway there. And then furthermore, there are other issues with power and size, and the problem increases with the sample size. So in terms of economic relations, if you don't consider this, your statistical inference can be wrong. So this is more, I'm going the wrong way. I was wondering why. Oh, this is the end. I did go back. So now we have to move to the... Is it time for... Not yet for tea. No. Is it 10 or 10:30? 10:30. Okay. I think we can get quite a bit done here. So for now, we're just going to focus on the ADF test, and then in a separate discussion, we will say, but how is the Phillips-Perron test now different? And the truth is, it will be very similar, but it may use a different way to in the augmentation to account for zero correlation. So we will discuss that. But just to get the concept and apply that, and then later on we can just see what other unit root tests bring to the table. So I'm not going to repeat many of these things. So we're either going to conclude stationarity or non-stationarity, and then we want to know whether it's I1 or I2. So we know that these are just still the reasons why we test for non-stationarity, and these are the properties. So this is, it's just sometimes a week or 2 weeks between when I see the student, so this is just a reminder. So what is a unit root? A unit root is simply the solution of that relationship. Think about the expression like even x minus 5 equals 0. What's the solution to that? X is? 5. Yes. A second degree polynomial like x squared minus 1 plus 6. How did we get the solution for that quadratic expression at school? What values of x will make that expression true? X. If we do, I don't know if I will be able to write here. So if this is now, so think about that case where we say x squared minus 1, what did I say? Plus 5 or 6? Yeah. So how, and then we need to solve it for values of x. So it's x minus 3 times x plus 2. So x can be 3 or x can be minus 2. And if you don't pick a nice quadratic expression, then you have to find those complex roots. So saying what is the root of the process is simply what will make the
The minus x.
where yeah, sorry. You see this is I can't remember when I last had to do that. So it is it's simply what will make this expression true for which value of rho and when then this solution will be 1, the root will be 1 when rho is equal to 1. And if that rho is then smaller than 1, the root will lie outside the unit circle, but that's a little bit a non-issue because we're just interested in how the series will behave. So this is just what we talk about when we talk about a unit root. So if that rho is equal to 1 or not. So in essence, and then in all the proofs and in the literature, since what we saw in that partial autocorrelation function, we saw that for most series, it's just AR1 process. So we only need really to look at the coefficient of the first lag. That's the one thing. And furthermore, the MA components have all of them have a constant mean. So they don't bring anything else new to the table in terms of trends. So that's why a unit root test, we don't have to lag the error term. The simplest form of the test is simply this. We've seen that as soon as we get close to 1, the series starts to drift. So basically all that we need to do is to do this regression that you can do with the most basic software. Any software that can do the simplest OLS, you can actually find the value for rho. But of course, it is a little bit more complicated. The distributions will be different. And also, yes, it is actually this. The test stat is literally the stat on that row. So the essence of a unit root, it is a regression. So it's all about the row, or perhaps it's all about the tau. And I know this looks a little bit like a big sale somewhere, but I don't know. There are a few things that I just want to highlight. So if we look at this, we apply it to that series. That is the growth rate of South Africa going back to the post-World War II. And I wish we can go back here to that kind of growth rates. So if you look at that, is that a mean reverting process? That you can see it's not always so easy. That's why we sometimes need a little bit of help from statistical tests. Because if you look at that one, it looks like it almost looked like there is a slight downward trend, or maybe a little bit of a break here when we started to see a lot of inflation and a lot of political uncertainty, and then some adverse things happening here around the global financial crisis and COVID. So in essence, one would think about a growth process as a mean reverting process subject to business cycle, behavior, etc. So we need that test. So actually that coefficient, how close is it to 1? It's a little bit far. So based on just intuitively look at that coefficient, we still have a couple of things wrong. It looks like it's not too close. It's closer to, it's substantially lower than 1. So that will make me, just at this stage, to favor that is a stationary process. This t-stat is, however, not what we need. It's not going to test the alternative that rho is smaller than 1. That is simply an indication it's different from 0. But that's not helpful in this case. So just putting it in a simple regression package is not good enough. You have to do a little calculation on the side then to know what the t-stat is for a one-sided test, different from zeros, from 1, smaller than 1. But we're getting there. It's not a difficult thing to do.
Sorry, Prof. On the previous slide, so I know not related, but why would you have a negative r squared?
I think there's no constant in here.
Surely 0?
I know. One sees it. Sometime, the other day I saw a panel result that's actually not that bad, and one of the dimensions, the within or the between, so one of those r squares was 0 as well, a negative as well, and I wondered what. But we do see it when we do it, some of the diagnostic testing as well, but that's a good question. I think we must just investigate a little bit. But intuitively, it feels that it's between 0 and 1, right?
Yeah.
Yeah, let's have a a closer look at that calculation, why it is negative. But a good observation there. We can see in this regression there's not a big problem with old-fashioned zero correlation. It's close to 2, but that is also beside the point. So here are some of the other tests that are readily available in the software. Most of them test non-stationarity versus stationarity. So now all of these are just doing things slightly different, using different ways. Some of them use non-parametric methods to correct for the zero correlation that may be in that regression, etc. We will point that out. So the first problem here is that t-stat compares the value, the rho to, in order to compare it to 1, we have to do a slightly different calculation. So you have to calculate that t-stat yourself by taking the parameter, subtract 1, divide by the standard error on the regression, and take that as the t-stat. But there would still be problems. So the hypothesis test is non-standard. That's the first thing to consider. That was maybe the second day when Dicky and Fuller discuss how they're going to do this. And then maybe on day 3, they looked at what are the distributions of that parameter, of that rho. And then they realize only when series are stationary if we bootstrap this distribution, and just at the bottom of that slide, you see the R code for bootstrapping this distribution. Just when we generated the series with the 0.5 there, and you bootstrap this distribution around the 0, then it looks like that we normally know. But if we generate that series with a 1 in there and bootstrap the distribution of the row, you can see it becomes skewed around 1, but highly skewed to the left. So even now we want to do a t-stat, but what will be the appropriate value for t? In this case, it's minus 1.96 plus 1.96. Or if we work one-sided, what is the 5% one-sided critical value? Minus, who can remember those F tables in the back of Wooldridge and Gujarati? It's then slightly, and not minus 1.96, a little bit minus. We can look it up. But a bottom line is that in this case, we just put the whole 5% on the left side. In this case, we also put the whole 5% on the left side, but because it's so skewed to the left, it will not be minus 1.96. It will, I think it's minus 1.645. That's a figure that now comes in my head. Maybe I'm like politicians that say inflation is down by bread prices came down, egg prices came down, and they just name a figure. I think it's minus 1.645. So everything to the left of that is then in the rejection region. But for this, that critical values become minus 3.4, minus 4.1. So much more strict to get 5% to the left of that. So we will see that. And now this so often goes lost in translation. In order to standardize the hypothesis test so that when we look at that result, we don't have to on the side remember that the hypothesis is that that row is equal to 1, but that t-stat is for row equals to 0. To get that done, one way of doing it is just to change the test regression slightly. And do you agree that subtracting the same number both sides, that's completely in order? So this will give us a delta yt on the left-hand side. And this, if we collect those two terms, it becomes rho minus 1. So now the null hypothesis is rho minus 1 equal to 0. But if you take the 1 to the other side, we're back at what we want. So that's why if you look at unit root output, on the left-hand side, it will have d of yt. And on the right-hand side, it has lag of yt. But it's just because we just did a little bit of mathematical manipulation to have the null what we want. So now we can look at that. If we run this regression, this rho minus 1, which we may call rho star if we want, or anything else. So if rho minus 1 is now equal to 0, it means the original row is equal to 1. Now we can test rho minus 1 equal to 1 or rho star equals to 1 against the alternative of smaller than 1. But what we actually do is to test that if the rho is in the original equation is equal to 1 or smaller than 1. So the test regression, we've just changed it a little bit, but in essence, that and that is mathematically exactly the same thing. It's just that the t-stat here will reflect the hypothesis that the original parameter is equal to 1 or not.
Sorry, Prof. I'm a bit rusty on my algebra. For line number 2, how do we get rho minus 1 there? I understand how we get rho, but where does the minus 1 come from?
If you collect those terms, there's a 1.
Right.
You don't see it, but it's there.
Okay.
So then you write yt minus 1, and then it's rho minus the 1.
Okay, all right. Thanks.
So why do we run 3 models? If you look at the bottom line, that's what we saw just now. So we can put it on top, it doesn't matter. But this kind of does not allow for series with non-zero means or deterministic trends when it's so moving up in such a systematic fashion that you can almost identify an underlying deterministic trend as well. For most economic time series, I think the intercept model would fit the data best. And occasionally the trend, to add a trend, helps a little bit, because if the trend is there and we don't include it, you actually have a misspecified model and this will affect this parameter. But just starting out, if you think about economic time series, we said sometimes it's difficult to distinguish between a trend stationary series, which is non-stationary, and a series with which is just a function of a trend. So they will look so similar. So we almost test. We have all of these 3 specifications to cover our bases. Many of the newer tests ignore the none model altogether. Yes.
So suppose we have 2 or 3 variables we are checking for whether they are stationary. And maybe one is the stationary when we include an intercept. Another is the stationary when we exclude both the trend and the intercept. Does that give us a headache with modeling?
I think how we should think about this. You focus on one series at a time, right? So the results can be mixed. So let's not go there and say, well, for this variable, it's stationary here, and for that variable, it's stationary there. You have to, in isolation, take a decision on each series before you move on to the other series. In the end, if your results are overall quite mixed and you don't know, you actually want to use both a stationarity, and now you pick this result here and you pick that result there. I don't say you cannot do it, but it's almost that you have to come to a conclusion about one series, just not thinking about what other series.
Okay, my challenge was after you have determined, say, okay, this series, we make a conclusion that it's stationary when we do not include a trend or an intercept. So I was thinking ahead to say, now when it comes to modeling, should you be worried that maybe one series is...
You address the problem at the point where you look at one series. Not thinking about what will income do when you're busy with money. So you think about money. And the first thing to do is basically to say, well, I know that real money will probably not be a mean reverting process. Or real GDP will be an increasing process. So you have that expectation at the outset. Sometimes some of those theories that go up and down, like bond rates or other interest rates, you don't know exactly. But when we consider bond rate, we don't think, but okay, what does repo do? You know, I have to take a decision whether bond rate is most likely stationary or non-stationary. So you think about it from a theoretical perspective, what are we dealing with? A growth process is likely, because of business cycle theory, a mean reverting process. Inflation rates, because of monetary policy, it will rise over periods, but then monetary authorities will intervene and bring it down. And then it may rise again. So from that perspective, if you have strong monetary policy in place, that will also be perhaps a mean reverting process. But exogenous events like the oil price shocks, etc., can make it to behave non-stationary. So you focus on that one series, and if sometimes you will find different conflicting results from the three tests, then you can say, well, perhaps just by looking at it graphically, I want to put more, attach more value to this result. And then you also look at 5 other unit root tests and see if they tell the same story. And at that way, come to a conclusion.
Yeah, that's me.
Where are we now? Now we can have a break. So when we come back, we discuss this. This is now almost the story, but there's one more problem. Just a slight problem. That this is still the ADF. This is still the DF. We have to make it ADF. Yes. Okay, so let's take a break until 11.